So in this strength of materials 1 subject, the contents to be covered in this lecture are: number 1, uniaxial stress on inclined planes, then biaxial stresses on inclined planes. So before enter into these topics, we just make a small reminder in the resolving vector quantities. So this thing we have already seen in the lower classes. Yes. First let us see this displacement quantities. It is one of the vector quantities. You see that there is a displacement d is equal to 28 mm in this direction. Let it can be resolved into horizontal and vertically with respect to this theta. Theta is subtended with respect to horizontal axis, and therefore when it is resolved into horizontally, it becomes 28 cos theta mm, like that. When it is resolved into vertically, which is 28 cos 90 minus theta, that is 28 sin theta. So like that, if we take the velocity which is here, see that there is a velocity which is there is a body or an object moving at a velocity v is equal to 17 meter per second in this direction. Let it can be resolved into horizontally with respect to this alpha angle, and vertically, so like it becomes like this. When it is resolved into horizontally, its velocity becomes 17 cos alpha meter per second, and when it is resolved into vertically, which is equal to 17 cos 90 minus alpha, that is 17 sin alpha, like that. Here a force quantity, a force which is acting in this direction, there is an angle gamma which is subtended with respect to vertical, and therefore it can be resolved into. So since here the angle is subtended, angle gamma is subtended with respect to horizontal, and therefore it can be resolved into vertically in cos gamma, therefore 21 cos gamma, when it is resolved into vertically 21 cos gamma. So here the theta is subtended about horizontal, and therefore it becomes, when it is resolved into horizontal, it becomes cos theta. Here theta is subtended with respect to vertical axis, and therefore now when it is resolved into vertically, it becomes cos alpha. Then when it is resolved into horizontally, it becomes 21 sin gamma, or 21 cos 90 minus gamma. And therefore next we see that moment, this moment a couple is acting in this direction at an angle beta subtended with respect to horizontal. Now when it is resolved into horizontally, it becomes 7 cos beta. When it is resolved vertically, it becomes 7 sin beta Newton meter. So these are all some of the vector quantities which can be resolved horizontally and vertically with respect to angle subtended with respect to either horizontal axis or vertical axis. Yes. So so far we just a small practice made on the resolving vertical vector quantities. Now only we enter into the subject. You see that uniaxial stresses on inclined planes. Yes. So we say that forces having magnitude and direction, because it is vector quantities. As we have already known, forces have magnitude and direction, but stresses have one more attribute, namely plane of action. At which plane it acts, either inclined plane or vertical plane or horizontal plane, either the stresses acting on x plane, y plane, z plane, or on inclined plane or vertical plane. So like that, the stresses has one more attribute, namely plane of action. So here you see that in figure A, so this is figure A, sigma x, there is uniaxial stress acting. Sigma x acts on face BC. This is BC phase. This phase is called as BC phase. Yes, on the area B into T. So this sigma x stress acting on the face BC of area, this is the vertical distance B, and this is the thickness T. So this face has an area of B into T, and therefore the same stresses acts an inclined plane EF. Let it be taken an inclined plane. Let us take an inclined plane. Yes, let us take an inclined plane. Oh, so before that, I would like to give small introduction about this chapter. Actually, why do we concentrate these stresses on inclined planes? So normally stresses acting on any plane, either it is vertical or horizontal. Before, initially we apply the force on horizontally or vertically on a member or on a plane. So this is the system that we apply. But because of this force or stress on this vertical or horizontal plane, what happened, there are infinity planes occurs. There are infinite planes occurs. So that are all called as oblique plane, inclined planes with respect to some x plane or y plane or principal axis. So anyhow we can refer any plane. You see that this is one plane. You see that this is one plane. Now the stress acting perpendicular to this plane, this is normal stresses, but our interest is to find what is the normal and shear stress acting on any inclined plane. So you see that we take a small plane here, EF is going here and here and here. So this is one kind of inclined plane. So we apply a magnitude of stress along this face or this plane, that is BC plane, sigma x. Now my interest is to find what is the normal and the tangential stress on this inclined plane due to the stress, normal stress applied on this vertical plane BC. So like that we can split infinite planes in plane vertical planes as well as the horizontal planes. We can also split horizontally, and we deal case by case. What is the effect? What is the change from when we apply the stress sigma x on this face vertically or on this face vertically, whatever may be, normal to this plane, but the effect, what is the effect on our interest plane, our interest any inclined plane? So that thing is going to find or in this chapter. You see that. So here there is a problem, sigma x which is acting on this plane BC, it is vertical plane, and vertical plane there is sigma x normal stress acting along x direction. So here now our interest to find the what is the normal stress on this plane and shear stress on this this inclined plane theta is referred with respect to x plane. Theta is this inclined plane is referred with respect to x plane at an angle theta. Okay, yes, let us start now. Here the applied force is same. You see that here the force acting on this plane is sigma x into b into t. This is force acting on this plane. Am I correct? Yes. But here let us take this EF inclined plane, this face. Here also the force is same, because then only the system will be said to be in equilibrium. Okay, let us take this system of stresses, forces, whatever may be. Here there is a force acting at this face. That force can be calculated as sigma x into b into t, and like that the same force is acting on this plane. Force are same or equal, but the stress differs. So you see that here the applied force is same, sigma x into b into t, but the stress would be different in this plane EF. In the since the plane area is in this inclined plane, the plane area is b by cos theta into t. It is not b into t, since it is an inclined plane. Therefore b is B is not B is equal to B cos theta. This dimension is B cos theta. It is not simple B. Whereas in this plane, this dimension is B. In this plane, this dimension is B cos theta into T. So like the, sorry, B by cos theta, B by not B cos theta, B by cos theta into T. Yes. Therefore, this stress on inclined plane is called as oblique stress. So this stress is called as oblique stress. Now the stress is different, so that stress is called as oblique stress. Let that stress be sigma x dash as shown in figure B. This is the actual stress, actual stress acting on this plane. When the stress acting on this plane is simply sigma x, when the stress sigma x becomes a sigma x dash on this plane since the area differs. Therefore, this this x dash is equal to nothing but we have an force equilibrium equation such that one of the force acting on this plane is sigma x into B into T, which is equal to the force at this plane is sigma x dash into B by cos theta into T. We just equate these two. From this we can find sigma x dash is equal to sigma x bt divided by B into T divided by cos theta, which is equal to sigma x dash equal to sigma x into cos theta. Therefore now we can write the stress acting on this oblique, that is oblique stress equal to, or stress acting on this inclined plane is equal to sigma, we can write in terms of sigma x, that is sigma x dash equal to sigma x cos theta. Yes. The next sigma x dash can be resolved along the normal to the face EF as now. So this is sigma x dash which is acting on the EF plane, and this is sigma x which is acting on the plane BC. This is oblique plane or inclined plane. So now let it be sigma x dash. Okay. Now what we are going to do here, the stress is being resolved into sigma as into sigma theta and tau theta, which are our required stress. That is, our interest is to find what is the normal stress acting on the E plane, what is the normal stress acting on this inclined plane EF, that let it be sigma theta, and what is the tangential or shear stress acting on this plane, let it be tau theta. So let us find that one. Sigma theta is equal to, we just resolve, that's all, we just resolve the this one. Sigma theta is equal to sigma x dash into cos theta, because this is the angle subtended. Theta becomes like this. Theta, this is the theta. You see that? This is angle subtended theta. Okay, actually when we draw a straight line, this is the reference of this plane with respect to x plane theta. Okay, and therefore this will be becomes theta, this one becomes theta, and therefore when it is resolved into the sigma x dash, when resolved into sigma theta, it becomes cos theta. Therefore sigma theta is equal to sigma x dash cos theta, and tau theta can be resolved into which is nothing but that is cos 90 minus theta, and therefore we have tau theta is equal to sigma x dash sin theta. Now we substitute sigma x dash is equal to, as our previous slide we have determined, sigma x dash equal to sigma x cos theta, and therefore let us substitute here sigma theta is equal to sigma x dash, instead of sigma x dash it is substitute sigma x cos theta, already a cos theta. In order to resolve this component, sigma x dash can be resolved into sigma theta, that is normal stress acting on the normal to this plane, which is equal to sigma x dash cos theta. Therefore sigma x cos theta into cos theta, which is sigma x cos square theta. Next, tau theta, what is the tangential stress? That is nothing but sigma x dash sin theta. Sigma x dash is cos theta, therefore sigma x cos theta into sin theta. Here a sin theta exists. So these two, that is sigma theta and tau theta, are nothing but what is the stress normal and what is the normal and shear stress acting or subjecting on this inclined plane due to the sigma x applied on this plane. Okay, so because of this sigma x on this plane, what is the normal and shear stress acting on this EF inclined or oblique plane EF? So that thing we have found. So in any uniaxial stresses, so this is the case, nothing but let us take a single plane. There will be a single direction stress sigma x only acting. So it is acting on vertical plane or horizontal plane, whatever may be. Because of this stress, what is the effect on an inclined plane? What is the effect on inclined plane due to the normal and tangential stress on this plane, on that inclined plane? So that normal and shear stress are sigma theta and tau theta. Okay, so we just refer that inclined plane with respect to x plane theta. So we just refer this one. So next let us see the biaxial stresses on inclined plane. So far we have here the previous slide we just saw the uh, a single plane. Just took a single plane. We just saw a stress acting on single direction, single plane, sigma x. Now yes, this is the case, single plane stress. Now we go to the biaxial stresses on inclined planes. So in this case, the normal stresses acting on both x and y planes. Now the normal stresses are subjected on both x direction and y direction. Okay, consider an inclined plane EF making an angle theta with the x plane. Now the same as in previous case, what we have done, we just took an inclined plane. EF with respect to horizontal plane, or with respect to x plane, with respect to this x plane. This inclined plane is referred with respect to x plane at an angle theta. It is subtended an angle theta with respect to the x plane. Okay, so this is the method of referring this inclined plane. Yes. Next, EF makes theta with x plane. So that's all. And let sigma theta 1 and sigma theta 2 are the normal stresses on this inclined plane EF due to the normal stresses sigma x and sigma y respectively. What we are going to do as per the principle of superposition, here what we are going to do, we just took the separate systems, we just split into two systems. One is we just disappear, or we just ignore the stress acting on y plane. So now there is only uniaxial stresses acting sigma x. So because of this sigma x, what is the normal stress on acting, normal stress that we can find along this plane EF, inclined plane? Let it be sigma theta 1. Like that, there is in another case we just split, that is split. In that case, we just ignore the sigma x. There will be only sigma y. So because of this sigma y, what is the normal stress on this plane? Let it be sigma theta 2 and its corresponding shear stress, so tau theta 2. Like that we can find. And finally, both systems, we just found the sigma theta 1 and sigma theta 2, and it should be make sum for finding the total normal stress due to this plane stresses on these two planes, x and y planes. Okay, that is plane normal stresses on this oblique plane, that is sigma theta is equal to sigma theta 1 and sigma theta 2. That thing we are going to find. First let us find sigma theta 1. Sigma theta 1 means here sigma theta 1 is nothing but the normal stress on this oblique plane due to this sigma x acting. Yes, it is obviously when this sigma x becomes here sigma x days. We know that, as in previous case, we know that that sigma x days is equal to sigma x cos theta, and therefore sigma theta 1 becomes sigma x cos squared theta. That's all. Like that, sigma theta 2 is equal to, since it is acting this plane sigma y, and therefore this is sigma y. And here the normal stress is nothing but sigma y into cos squared into theta plus 90. So and therefore sigma y sine squared theta. Otherwise we know that sigma y dash is equal to sigma y. So because of this sigma y, here the sigma y, whereas when it comes to here it is becoming sigma y dash. This sigma y dash is equal to sigma y sine theta or cos 90 plus theta, and therefore in order to find the sigma theta 2, which is equal to sigma y dash cos theta plus 90 or sigma y dash sine theta, and therefore finally it becomes sigma y cos squared theta plus 90 sigma theta 2, which is equal to sigma y sine squared theta. Hence now we find the total normal stress on this oblique plane due to the normal stresses acting x and y planes, that is sigma x and sigma y, are sigma theta is equal to sigma theta 1 plus sigma theta 2, which is equal to sigma x cos squared theta plus sigma y sine squared theta. Yes, and let us find the shear stress. So when we are going to find, similarly tau theta 1 and tau theta 2 are the tangential stresses on inclined plane due to the normal stresses sigma x and sigma y respectively. So it's the same as we as the previous case that we have solved, the same method is being used. How how did uh, how did I solve this one? Again we just neglect the the sigma y part when we consider the sigma x. So like that, and then next we just neglect the sigma x part when we considering the sigma y part. So in which case tau theta 1 becomes sigma x cos theta and sine theta. So because before we see that there will be when the tangential stress becomes tau theta 1, yes, in the previous case that is sigma x cos theta and sine theta. Like that sigma theta 2 is sigma y cos theta plus cos of theta plus 90 into sine of theta plus 90, and therefore it becomes minus sigma y cos theta and sine theta. So like that we just found these two, tau theta 1 and tau theta 2, because it is vertical y, but the it is the oblique plane is referred with respect to x plane, and therefore it becomes sine sigma y cos theta minus theta plus 90, and this is sine of theta plus 90, and therefore minus sigma y cos theta sine theta, and then finally tau theta is equal to sigma x minus sigma y. When we add these two, tau theta 1 plus tau theta 2, it becomes sigma x minus sigma y into cos theta into sine theta. Yes. So next, biaxial stresses on inclined planes, but the difference of the previous one and this case are whereas there only the normal stresses acting on two planes. Here in addition the shear stresses are also acting on this all planes or on two planes. You see that in the first case, I just want to summarize. In the first case there is only one plane stresses sigma x acting. Because of the sigma x, what is the sigma theta and tau theta on this oblique plane EF. Okay, and the next case then the sigma x and sigma y, both two stresses, normal stresses acting on two planes, perpendicular two planes, and this because of these stresses acting on these planes DC and the BC, what is the normal stresses acting on this EF inclined plane, that is sigma theta and tau theta. Okay, now somewhat extended, not only the normal stresses acting on these two planes, but also the shear stresses are also acting. So now our interest to find the same, what is the normal stress sigma theta on plane oblique plane EF, and what is the tangential stress acting on the oblique plane EF. So that thing we are going to see in this area. So Let us take a plate ABCD of unit thickness. The plate has unit thickness, very important. The one dimension let us fix as unit. Okay, yes. Then here AB is, let this one be the AB. AB is equal to CD. Since it is rectangular plane, AB is equal to CD is equal to dimension is B. Like that, BC is equal to AD is equal to its dimension BL. Okay, it is given. Next, let us take here sigma x, comma sigma y and tau xy also acting on x and y planes. Okay, yes. Then our aim is to find the again sigma theta and tau theta on this inclined plane EF. For that, consider this triangle EFG. We just take the triangle EFG. Next, on the face FG, you see that this is, we just took that triangle individually, EFG. Yes, in this case, on the face FG, stresses are sigma x and another one is tau xy. So these are all the input stresses or given stresses. Nice. The forces are in the face FG. The forces are, one of the normal force is sigma x into B into 1. The 1 means unit thickness. Okay, like that. And another shear force tau xy into B into 1. Am I correct? On the face EG, next let us go to the on the face EG. So we just find the force on this face or on this plane FG. Okay, one of the normal force sigma x equal to stress into area sigma x into B into 1, and another force shear force on this plane acting FG is equal to tau xy into B into 1. Okay, same thing. Let us take on the face EG, the stresses are sigma y and tau xy. So these two stresses acting on this face EG. Yes. Now the forces on the face EG are, one thing is sigma y into B sin theta by cos theta, and the another force is sigma y tau xy into B sin theta by cos theta into 1. So this is nothing but we see that otherwise the area of EG. First let us find the area of EG. In the face EG, what is the area acting? In the face FG, area is nothing but B into 1. That's all. In the face FG, the area on this face FG is nothing but B into 1 because unit thickness. Okay, yes, but in the area of EG, the area is equal to, what is area? We have to find this length, this side length. This side length is B and this length is, what is this length? This is nothing but B into tan theta. As per this trigonometry, this is theta. You see that this is theta and this will be the opposite. This is the adjacent. So from which B is equal to this side EG is equal to what comes? It is nothing but B tan theta and into 1, unit thickness 1. Therefore the area of EG is equal to B tan theta or B sin theta by cos theta. The forces on EG are sigma y. So now let us find force. Here we have determined force for FG already. Like that, on the face EG, we are going to find the force on the face EG. For that, you see that the force is nothing but, first stresses acting on this face is again sigma y and tau xy. So for that let us find force. The forces on EG are, one of the force, normal force is sigma y into B into sin theta by cos theta into 1. Okay, another one is the shear force is nothing but tau xy into B sin theta by cos theta. Yes, these two forces acting. Now forming force equilibrium equation, we just equate these two. Okay, from with respect to this inclined plane, yes, as we have already discussed, when this sigma x, this direct stress
its effect is given to this inclined plane as sigma x dash. Am I correct? And like that, tau xy is giving an effect on this inclined plane as tau xy dash. Okay, like that, this sigma y is giving an effect to this inclined plane as sigma y dash. Like that, this tau xy is giving on this inclined plane as tau xy double dash. So like that we split the stresses. These stresses are all here. The sigma s becomes sigma x dash on this plane, and this sigma tau xy becomes tau xy dash on this plane. Okay, like that, the sigma y becomes on this plane sigma y dash inclined plane, and tau xy becomes on this plane tau xy double dash. Okay, now let us find forming force equilibrium equation. First let us equate this sigma x into b into t, normal stress, which is equated with this force sigma x dash into b by cos theta. Okay, sigma x dash into b by cos theta, and therefore sigma x dash is equal to sigma x cos theta, as previous cases. Same as previous cases. Next, tau xy dash is equal to what it comes, tau xy dash is equal to tau xy cos theta. Okay, like that, sigma x dash is equal to sigma x cos theta, and tau xy dash is equal to tau xy. When you resolve into here, it becomes tau xy cos theta. Okay, similarly, sigma y b sin theta by cos theta is equal to sigma y dash b by cos theta. Sigma y dash, this length of this inclined plane is b by cos theta. This is the inclined plane. Its length becomes b by cos theta. This is b tan theta. This is b by cos theta. And therefore, sigma y dash is equal to sigma y sin theta. When equate these two, what happened? Sigma y dash equal to sigma y sin theta, and tau xy double dash is equal to tau xy sin theta. Okay, same. Now let us find sigma theta. Now we have determined all these inclined stresses. What are these stresses acting on these inclined planes? One is sigma x dash due to sigma x, another one is tau xy dash due to this tau xy, that is here, and another one is sigma y dash due to this sigma y on this inclined plane, and another one is tau xy double tau xy dash tau xy is tau xy double dash on this inclined plane due to this tau xy. We have determined all these four stresses. Next, simply we are going to resolve. How will it be resolved? Let us see in the next slide. Yes, you see that this is sigma x dash and this is sigma y dash. Our interest to find sigma theta. Now we must know what is the angle in between these all forces. We must analyze that point. We know that this sigma x dash is subtended at an angle theta with respect to sigma theta. Okay, this is normal stress, our interest to find, and therefore this is 90 minus theta, because these two are normal. Sigma is normal plane stresses, sigma x dash and y dash. When it is an angle sigma theta is referred at an angle theta with respect to the sigma x dash, therefore this is 90 minus theta. Okay, like that, this is tau xy. This sigma theta and tau theta are normal. Okay, when it is the if it is this angle is 90 minus theta, and therefore it becomes theta. Am I correct? Like that, when this angle is theta, sigma theta and tau theta are normal 90 degree, and therefore this angle is 90 minus theta. That's all. Now let us solve. You see that sigma theta is equal to this sigma theta is equal to this sigma x dash bring to here at an angle theta. Therefore it comes sigma theta is equal to sigma x dash cos theta. Okay, we just simply resolve. Okay, because theta at here. Okay, when it is resolved into sigma theta, it becomes sigma x dash cos theta. Okay, then what about sigma y dash? This is sigma y dash is 90 minus theta, cos of 90 minus theta, therefore it becomes plus sigma y plus, you see that this is the direction, sigma x dash direction, this is sigma theta direction, so both are same direction. When like that sigma y dash, this is the sigma y dash vertical stress direction, when it resolved into here, what happened? Again it comes this direction, therefore both are plus. Okay, like that. Now there will be, you just refer this figure, just refer this figure. So in this case the same sigma theta, this there are tau x y dash, this downward direction, and there are tau x y double dash. Okay, uh, yes, the stresses on these inclined planes. Okay, we just resolve it with respect to this sigma theta. Okay, with respect to this sigma theta, first let us resolve. This is the theta angle, tau x y double dash is theta angle with respect to this sigma theta, and therefore what comes? Tau x y double dash cos theta minus tau x y minus, because the tau x y double dash direction is this direction, but sigma theta is this direction, opposite direction, and therefore we put sign minus, minus tau x y double dash cos theta. Here tau x y dash is 90 minus theta with respect to the sigma theta, the angle, it is inclined at an angle 90 minus theta, and therefore what comes? Tau xy dash minus tau xy dash, because it is downward, when it is resolved with the sigma theta, it becomes opposite to the sigma theta, and therefore that sigma theta value, this tau xy dash is changed as tau xy dash minus tau xy dash sin cos 90 minus theta, or tau xy dash sin theta minus tau xy dash sin theta. That's it. Now sigma theta has been resolved. Okay, so let us substitute. Sigma theta is equal to sigma, we know that sigma x dash is equal to sigma x cos theta, and therefore let us substitute that one, it comes sigma x cos y theta plus sigma dash y sin theta. We know that sigma dash y is equal to sigma y sin theta, and therefore sigma y sin square theta minus, we know that tau x y dash sin theta is tau x y dash is equal to tau x y cos theta, therefore it becomes tau x y cos theta into sin theta, like that. We know that tau x y double dash is equal to tau x y sin theta, therefore it becomes tau x y dash tau x y sin theta cos theta. When sum these two, it becomes minus 2 tau x y sin theta cos theta. So this is the formula to be required for find the normal stresses on this inclined plane due to the sigma x and sigma y acting on two planes. In addition, tau xy is also acting. Okay, this is the formula to be used. Next, tau theta. Tau theta, how can we find this tau theta? Again, let us take this. We just resolve all the tau stresses with respect to this tau theta. Here only tau theta. We just resolve the tau x y dash stresses component into tau theta component. We just resolve. Okay. Here you see that first let us take the tau x y dash. So this is angle theta. Okay, and this is downward, and this is also towards downward direction, and therefore positive. Therefore tau x y dash cos theta. Then whereas let us see tau x y double dash, when it is resolved with respect to 90 minus theta, so it is resolved when it coincides with this tau theta, therefore its arrow is towards this side, it goes upward direction, whereas tau theta is downward, therefore it becomes minus. Therefore minus, you see that minus tau x y dash into sin theta, because 90 minus theta with respect to this tau theta, this tau x y dash is an inclined at an angle 90 minus theta, therefore tau x y double dash cos 90 minus theta, or tau x y double dash sin theta, it should be minus, because it is when it you just position here, when it coincides with this tau theta, it goes upward, whereas tau theta is downward, and therefore it is negative. That's all. Then when comes to here, the sigma x dash should be resolved into tau theta, okay, and this angle is 90 minus theta, and therefore so it is downward. It is also when it is resolved into tau theta, okay, when it is merged with this tau theta, this is also the same direction, and therefore this is plus. Therefore plus sigma x dash into cos of 90 minus theta, or plus sigma x dash sin theta. You see that plus sigma x dash sin theta, and here the sigma y dash, it is theta, but when it is resolved into this tau theta, so it is showing this direction, opposite direction to tau theta, and therefore minus sigma y dash cos theta. Therefore it comes tau xy into let us take, we just substitute tau xy dash is equal to tau xy into cos theta, like that. Tau xy double dash is equal to tau xy sin theta, and therefore when substitute here, take outside tau xy, cos square theta minus sin square theta, plus these two are sigma x minus sigma y, because sigma x dash is nothing but sigma x cos theta, and here sigma y dash is nothing but sigma y sin theta. Let us take sin theta cos theta, sigma x minus sigma y, cos theta sin theta outside, therefore it becomes sigma x minus sigma y, and therefore tau theta becomes tau xy into cos square theta minus sin square theta, plus sigma x minus sigma y cos theta sin theta. So when the trigonometrically we can solve further using trigonometric formula, the sigma theta becomes sigma x, this equation become, this formula becomes sigma theta is equal to sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 into cos 2 theta minus tau sin 2 theta, like that. This tau theta formula, when we apply this some trigonometric formula tricks and the formula, it becomes tau theta is equal to sigma x minus sigma y by 2 sin 2 theta plus tau xy cos 2 theta. Yes, this is the final formula that we found from this plane.